Hi guys, Janus here. Welcome back. In this exciting two-part special, I'm going to be covering everything you need to know about smooth muscles to start making gains faster and safer, and utilize all of this today. Before I can start talking about some of the more complex materials, however, I'd like to cover a bit of anatomy since it's going to be really important to understanding key concepts later on. Behind me here, I've drawn a pair of smooth muscles, one that is stretched out and another that is contracted right here. I'm going to explain a bit of this anatomy and then we're going to start moving on to actually looking at the contractile mechanism itself. Alright, let's get to it. Okay, so we're going to start from the outside and move inward. Along the outside here, you see the calcium ions. Now some of you might actually notice that I've drawn some arrows right here, and then of course here and here on the one next to it. These arrows, as I'm sure some of you already guessed, count for flow. So in this case, calcium ions are flowing towards the smooth muscle cells because they are relaxing. So the pressure inside the smooth muscle cell is less than the pressure outside the smooth muscle cell. So things are being drawn inwards. Then, some of you might have noticed these odd little protrusions along the cell wall. These are actually called gap junctions. Gap junctions are how smooth muscles exchange intra and extracellular materials, specifically, at least in this case, the calcium ions. These can come both internally and externally, but that will be covered later on when we look at contractile mechanism parts. Then, right in through here, we have something called a dense body. Now, dense bodies serve as a point of anchor both internally and externally. Allow me to show you. Notice right here, 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 and then of course in through here. The smooth muscles have actually attached themselves via their dense bodies. Dense bodies are an incredibly important structure because they help smooth muscles do something called stretch sensing. Say something happens to this smooth muscle cell. This one, because it's connected by their dense bodies, is going to feel it whenever their muscles start undergoing a stretch, whenever they contract, relax, etc. And then, of course, we've got these squares that I've drawn because, well, I ran out of colors. These are actually called plaques. Plaques are different from dense bodies in that they don't help smooth muscles attach to each other, but they do help attach the muscle fibers to the cell walls itself, so that way it can do its job more effectively. Then, of course, I've tried, but I don't know if the camera's going to be able to show it or not. I've tried drawing these as different colors. We've got different color here, and then a different color going this way. Smooth muscles have two muscle strands that spiral around the cells in opposite directions. As you can imagine, this makes for quite an intriguing contraction, but more on that later. Then, as we see right through here, we obviously have the nucleus. Now that I've covered a bit of the anatomy and I've explained a few of the key structures that are going to be really important later on, I'm going to go ahead and get into the muscle contractile unit part. Unlike skeletal muscles that have their thick and thin filaments arranged in large clusters called sarcomeres, smooth muscles possess sliding filament rails that spiral around the cell. Note how long the thin filaments are in comparison to the thick filaments, along with how they hang off the mechanism when fully contracted or max out the structure when fully relaxed. One of the neat features of this sliding filament rail system is that it possesses all of its contractile powers, regardless which position they happen to be in whenever a stretching force occurs. So long as the filaments are not separated by an unusually strong stretch and therefore damaged, smooth muscles can retain full functionality as opposed to skeletal muscle fibers, which lose their contractile force beyond a certain degree of stretch naturally. What's even more impressive is how smooth muscle contractile fibers differ from skeletal muscles. Unlike skeletal muscle fibers that weaken as a given static strain is prolonged, smooth muscles are capable of locking themselves at a given stretch and thereby dramatically reducing their energy consumption by several orders of magnitude, holding their position for hours without any difficulty. This works by merit of a hard mechanical on-off switch in relation to contraction and relaxation. More impressive still, smooth muscles are capable of decoupling at the first sign of additional stretch and lock themselves in place once more in a matter of seconds when stretching stops. It is this feature that makes smooth muscles so effective as a liner for hollow organs which often work non-stop or require storing various bodily fluids and materials for prolonged periods of time. Something that I simply did not expect about the sliding filament rail system was how strong it was when it was scaled up. Smooth muscles, pound for pound, are anywhere from about 2 to 3 times stronger than skeletal muscle and, of course, way more energy savvy. Now that I've covered a bit about smooth muscle contractile fibers, let's take a look at some of the additional structures around the nucleus. For the purposes of this discussion, I'd like to talk specifically about the sarcoplasmic reticulum, which I will be referring to as the SR from here on out. While I really wanted to be able to draw this behind me, I simply don't possess the artistic ability, so I decided simply not to try. It was bad. But anyway, unlike skeletal muscles, which have a large and elaborately designed SR for calcium storage, smooth muscles have a sarcoplasmic reticulum SR with a relatively small calcium storage capacity. Whenever I first studied skeletal muscles, this bothered me for some time until I began understanding more about how the extracellular spaces and the smooth muscles operate together. Unlike skeletal muscles, which rely primarily on calcium stores for muscle contractions, smooth muscles rely on their stores primarily to spark a contraction. Whenever a smooth muscle initially undergoes a stretching force, a mechanochemical series of events is kick-started that causes the release of intracellular calcium stores, which then bind to the cell's contractile mechanisms, causing a contraction. What follows is an incredibly simple and yet breathtakingly profound domino effect, which starts as a localized destabilizing event that causes contractions to ripple outwardly due to smooth muscles' dense body-based stretch sensing. All of these factors come together in a beautiful harmony, resulting in wave-like or pulsing contractions which are needed in places like the digestive system and our miles of blood vessels. Now that I've covered a bit of anatomy, it's time to start getting into the fun stuff. Smooth muscles must be able to relax and contract in a manner that allows for the greatest three-dimensional changes in volume, but also maximal power. These crucial requirements have led to an intriguing design. The picture behind me here, I've attempted to draw in such a way as to help differentiate between the two muscle fibers. But as stated prior, the colors are a bit off. We've got one strand going this way and another going that way. We know from studying skeletal muscles that muscle fibers can be stacked end to end or side by side. In either case, smooth muscles are designed to exploit this principle. Whenever a smooth muscle contracts, the fibers work against each other in one dimension, but then work together in another to cause a corkscrew-like twisting motion as it expands or contracts, as we see right here. Continuing the thought, smooth muscles must be able to minimize the space taken up while contracted and then maximize the volume when relaxed. To achieve these twofold requirements, a twisting motion becomes ideal. By twisting, smooth muscle layers or bundles are able to effectively fold into themselves, drastically reducing the space they occupy while also maximizing force potential. Unlike a more straightforward contraction, by adding additional dimensions to a motion, a greater amount of force can be generated in a much smaller area. So, how can this information be applied practically and made immediately usable? Before I can answer that question, I've got to double down a bit, do some more reviewing, share a few more important aspects regarding smooth muscle cells, and after that I'll be delving into the more complex aspects of smooth muscle building. Number 1. Smooth muscles involuntarily contract. What this means is that smooth muscles are not innervated in a fashion that allows for direct control, therefore they must rely on other means of responding to stimulation. Number 2. They attach to one another by special structures known as dense bodies. The contractile units inside smooth muscles attach to these fortified points along their outer wall and then attach to one another by these structures. This design allows smooth muscles to easily sense any changes in their environment. What's more, this design allows smooth muscles to easily create three-dimensional structures that are able to respond perfectly to a myriad of forces. Number 3, pound for pound, they're just as strong as skeletal muscle, if not stronger. Because smooth muscles are not under our direct control, it's easy for us to underestimate exactly how much power they can generate. If you'd like a quick proof of concept, while your member is in a flaccid state, attempt to pull it out to its full length. The resistance you feel is almost entirely from your smooth muscles. Number 4, they're capable of hypertrophy and hyperplasia. Similar to skeletal muscles, smooth muscle must be capable of proactively responding to increases in strain or workload by increasing their contractile strength. Subsequently, whenever the workload continues to rise, smooth muscles can rapidly increase DNA synthesis and then slowly twist themselves in two. This method allows an organ made out of smooth muscles to maintain structural integrity and grow at the same time. Number 5, they're chemically and mechanically reactionary. Since smooth muscles are not under direct control, they require more simplistic, though equally effective, means of responding to stretch or changes in environmental chemistry. Number 6, they retain full contractile strength and functionality even at maximum stretch. Smooth muscles must be capable of not only responding individually, but as a whole. This often means that smooth muscles have to serve as both points of resistance and contraction. This twofold purpose means that smooth muscle contractile fibers cannot have gaps in functionality, lest they be rendered useless in the face of an intense stretch. Moreover, in the event of an intense and prolonged stretch, special mechanisms along the length of the contractile fiber allows for a type of locking. Quite literally, smooth muscle contractile fibers will lock themselves in place in order to add even greater resistance and avoid pointlessly tiring themselves. If you are currently using a static as opposed to dynamic means of exercise, such as prolonged stretch, please review this point immediately. Number 7, they exhaust slowly. Smooth muscles are under constant stress from one force or another. This has led smooth muscles to develop an inordinately high tolerance to sub-maximal workloads in terms of stretch. While this does not carry over as effectively to greater bouts of strain, such as the exercise I will describe later on, they are still able to tolerate an impressive amount of stress, which can make them particularly troublesome to stimulate properly. Lastly, number 8, aerobic-based functionality. Smooth muscles require a rich and plentiful supply of oxygen and nutrients to maintain the ability to properly respond to stressors. While this requirement is not nearly as immense as skeletal muscle, they still account for a fairly large percentage of our basal metabolic rate. More importantly, this supply of nutrients and oxygen must be nearly constant, with interruptions being measured in seconds, not minutes or hours. Now that I've covered some of the relevant anatomy, did a bit of reviewing, and gave some worthwhile perspectives on smooth muscle functionality, it's time to get to the heart of smooth muscle building. Ladies and gentlemen, allow me to introduce you to something known as the Bayliss effect. The Bayliss effect is an innate property of all smooth muscles. This universal fact allows them to respond in a highly orderly and dynamic way to any kind of stretching or distending force. Changes in pressure or environmental chemistry are a daily constant in the life of a smooth muscle cell. This means that the Bayliss effect mechanism must be designed in such a way as to take into account these changes and respond effectively. In the case of pressure, whenever internal pressures fluctuate in a smooth muscle cell, the Bayliss effect mechanism responds by either opening or closing gap junctions along the outer walls of the cell. Remember, those are the structures I talked about towards the beginning of the video. Smooth muscles require calcium as a means of sparking a contraction and must be capable of repeatedly resisting such forces. Keeping this in mind, the Bayliss effect mechanism is also capable of another, though more complicated, response to repeated bouts of stretch. Instead of expelling calcium at the same rate, it narrows the gap junctions to allow for a greater resting retention of calcium, which offers a greater resting contractile force. With proper stimulation, smooth muscles can be encouraged to offer greater resistance to stretch and therefore more easily stimulated for the purposes of eliciting a supercompensating response in terms of hypertrophy and hyperplasia. In order for smooth muscles to be capable of responding in concert to a stretching force, they must be sensitive to changes in their environment. Specifically, changes in the concentration of various key minerals such as calcium. Should a greater availability of calcium be outside the cell, the Bayliss effect mechanism allows for a higher influx of this important element by further dilating gap junctions. This is a very important and appropriate response when we consider that millions of smooth muscles are actively exchanging intra and extracellular materials when a stretch occurs. Should a neighboring smooth muscle cell be undergoing a greater amount of stretch or stress, it will release intracellular calcium stores from its sarcoplasmic reticulum to recruit neighboring cells in an effort to lessen the amount of force being placed upon it. Just to simplify things a bit, I'd like to share a streamlined version of the Bayliss effect mechanism in action. Number 1, a force distends the cell. Number 2, internal pressures decrease. Number 3, gap junctions widen. Number 4, extracellular calcium is drawn intracellularly by merit of pressure differentials. Number 5, internal pressures begin stabilizing. Number 6, calcium levels inside the cell rise. Number 7, calcium attaches to receptors on the contractile units. Number 8, contraction occurs over a matter of seconds, about 5 to 8 seconds, give or take, before it really starts kicking in. In certain cases, though, this can actually be quite a bit faster, but that's a different topic for a different video. Then number 9, whenever this contraction occurs, internal pressure increases. Number 10, unused materials, including calcium, are then forced out of the cell. And then number 11, the process resets and begins anew the second a stretch is placed once more on the smooth muscle or layers of smooth muscle. As many of you may already know, a larger abundance of smooth muscles equates to a greater expansion potential. The more smooth muscle mass, the less collagen seems to be present, appearing to switch to a more favorable elastin-based structuring. This translates to significant changes in size under various degrees of relaxation or contraction. Take, for instance, the male member, which almost triples in overall volume when erect. Large increases in volume are indicative of healthy smooth muscles and a testament to their three-dimensional functionality as contractile units. Conversely, a lower amount of smooth muscle content defaults towards fibrosis at a much more limited range in terms of expansion capabilities. Smooth muscles can naturally break down and secrete collagen. Smooth muscles secrete and wrap themselves in varying levels of collagen or elastin as a means of creating a living stratum. In this way, they provide highly functional three-dimensional shapes. This capability is the primary reason they can be found in complex organ clusters such as the digestive system, reproductive system, and the endocrine system. Smooth muscles must have a rich and constant supply of oxygen in order to function properly. Without an abundant source of nutrients and oxygen, smooth muscle undergoes a bizarre metamorphosis in that they cease working as a contractile-based unit and instead switch to a collagen-secreting phenotype, which quickly begins depositing materials in the extracellular matrix. As this deposition continues, the secreted collagen will begin pulling on the surrounding structures to strengthen that bond. When this natural occurrence goes out of control, it can lead to all manner of unfortunate outcomes. In regards to the sexual organs, this can directly cause a loss in size or irregular distensibility, often expressed as curvature. In more extreme cases, like what occurs in Peyronie's disease, this can express itself as, say, an hourglass figure or further degrees of misshapenness in regards to the corporate chambers. Keeping in mind smooth muscles' propensity to switch to this undesirable synthetic phenotype, I believed my very first task was to devise a means of reducing this likelihood as much as possible and maybe even attain some additional benefits along the way. It was from this line of thought that the Angion method was born. That said, it was very far from my very first attempt. It's now that I would like to share the other two methods that I devised before creating the Angion method. Taking into account all I've learned about smooth muscles, I believed that applying a cyclic stretch of some kind would be ideal for causing calcium exchange and therefore smooth muscle contraction, which is needed to spur their growth. Towards this end, I examined the three chief forces a blood vessel undergoes daily. These three forces are circumferential strain, axial strain, and then of course shear stress. Initially, I completely overlooked manipulating blood vessels directly and opted for a much more general technique that relied on creating areas of high and low pressure within the corporate chambers. I called this technique the oscillator. The oscillator works by using both hands to apply a compressive force in an alternating fashion to move blood back and forth inside the corporate cavernossal chambers directly, thereby applying both a circumferential and shear stress-based force simultaneously. While this approach worked beautifully, and I did see some gains from it, I quickly lost them due to the underdeveloped arteries I mentioned in my very first video. That said, that failure would pave the way to creating the Angion method, since this technique had overt elements of shear stress which I believed could be refined. Similarly, working from an axial strain-based perspective, I devised a modified version of a commonly implemented wrist wrapping technique I believe is called an A-stretch. By wrapping my fingers just under my glands and then bending my flaccid member over my opposite wrist, I began applying a cyclic stretch by rolling my wrist in the opposite direction to transiently increase the stretching force applied to one side of my corporeal chambers for a bout of time ranging anywhere between 5 to 8 seconds. I chose this amount of time because it seemed to fall in line with how long it took my smooth muscles to begin actively resisting a stretch before locking themselves in place to conserve energy. After the 5 to 8 seconds would elapse, I would then relax the stretch for a few seconds so that way they could start actively contracting, and then I would reapply the stretch to start the whole process over again. Typically, I would do this 10 times for a total of 8 sets, or 4 sets per side per corporate chamber. Additionally, I would perform this on a 1-on, 2-off schedule. Similar to the oscillator, I saw gains from utilizing this technique, but this time I didn't lose them right away, thankfully. While I did not see any changes in BPL using this method, I did see a fairly quick difference in bone-pressed flaccid stretched length versus bone-pressed erect length, approximately 3/8 of an inch. At the time of implementing these two techniques, I was basically around the same dimensions I was when I began the Angion method training protocol quite a bit later. This meant that on a good day, I could stretch my member a fair bit beyond 7.75 inches. That said, I did lose a good portion of this stretch flaccid length from ceasing all training for a while when my life had really picked up and my research had stalled out. It's only been after reaping the benefits of the Angion method that I've decided to dust off these earlier prototypes. Before, my biggest personal setback was my underdeveloped arteries. Even when I was using proper technique, the blood flow simply wasn't there to support any real tissue growth. Having realized this painful fact, I began toying with the idea of seeing how well these could synergize with the Angion method and my new and improved blood flow. I'm happy to say that after a bit of experimenting, I found them to be a smashing success. Unlike other techniques that have the unfortunate habit of blowing out newly formed capillaries spurred by shear stress, I found these two techniques to be an absolute dream for providing the tailored stimulation I wanted and none of the unnecessary risks I didn't. As promised, this video is a two-part special. Go ahead and click the link right over here and go on to the next video.